like 11 different things going on inside my computer right now. All right, so guys, this is where I believe we are. So allow me to sort of help us get our arms around where we left off. And then guys, what you're gonna see is once we understand what enthalpy is, and I'm gonna approach this as if we've talked about it, but not fully embraced it. Then guys, we're going to talk about something called thermochemical equations, which is where we should have got to last time, but didn't because I didn't want to rush. And then thermochemical equations then become a bridge into what we're going to do next. Now guys, what you're going to see is the material that we are going to cover next, it should be the day's material, we may break in half. But we will get to the part of this that you need to know in order to be able to do the next lab, and all the bits will come together well. So, guys, joining me around what we have here on the board, here's what we're saying. We said, guys, that when we do chemical reactions, we are going to do chemical reactions in these mystical, magical containers that we call open containers. But guys, we also said that that is not contradictory to call these things closed systems. So let's talk. So guys, what does it mean that this circle is a closed system? What gets in and out? Energy. What doesn't get in and out? Mass. Okay, so how does energy get in and out of this closed system? Right there, right? So guys, that's the connection. That energy can get in and out of this system in only one of two ways. We got heat and we got work. So now let's focus on work. And guys, we talked about this idea that chemical reactions do work by doing what? They expand. And guys, that was central to what we talked about last time. So guys, if you don't understand this, you may want to scratch this into your notes, even though it's not on the screen. Guys, chemical reactions do work by expanding. I'll give you a second to write it down if you need. But guys, chemical reactions do work through expansion. You guys sold on that? Because the next point is even more important than the first. You guys good? Chemical reactions do work through expansion, yeah? Okay, but guys, that's not enough. It is not enough for something to be expanding to meet the requirements for work. So what are all of the requirements for work? We need movement, we need a resisting force, and then we need a force that is overcoming resistance and causing movement. So guys, if any of those things are missing, we're not doing work. So we talked about the idea that this is not work. I am exerting a force, the table's pushing back, but this is not work. How come? There's no movement. And guys, that's the obvious way to negate work. But the other way that we can negate work is by negating resistance. And that is what a constant pressure container goes. So guys, if you've ever blown up a balloon, that takes work, right? Because you've got the balloon that wants to stay small, it's elasticity, and you literally have to do work to get the balloon to expand. And guys, that's the same work that chemical reactions do. The difference is that we have these mystical, magical things called constant pressure containers. And how do they get rid of work? What do they get rid of? Resistance. So guys, these offer no resistance to expansion. Because there's no resistance to expansion, the reaction cannot do work. And if we get rid of work, then the only way to exchange energy is through the avenue of heat. You comfortable with that? Okay, now, what then, guys, do we call heat in the absence of work? That's the idea. Anything there that we need to talk about? You guys okay? What about this? Just a second, Tucker. Do these constant pressure containers exist in practice? Yeah, it's just an open room. So guys, if we carry out reactions that are trying to expand, and if they can freely expand into the room, technically the pressure does go up a little in the room, but we're really talking about the universe because the school leaks, and functionally there is no work because there is no resistant change in pressure. Is that okay? Go ahead, Tucker.
That was actually my question.
Okay, yeah. That good? That good? Guys, was that review helpful? Did that bring some ideas together? Does that sit better? Okay, so now guys, we're going to focus in on this idea that enthalpy is heat in the absence of work. And actually, we should remind ourselves of this. Remember, Q is heat, and H is the abbreviation for enthalpy. I know. It wasn't up to us. So here then is what we know. Guys, enthalpy by definition, have we done this yet? Is this where we're starting? We have. So enthalpy is heat exchanged in the absence of work, which is heat exchanged under constant pressure. It is abbreviated H, which we don't like. And now, guys, we can finally have a conversation that you may remember I tried to rush into, and then I was like, no, we need to slow down. So now we can have this talk. Guys, when we talk about enthalpy, what we actually talk about is changes in enthalpy. And guys, when we talk about change is always final minus initial. Good. Okay, so guys, what about this? What if we carry out a process and the final enthalpy of the system is bigger? Did energy go in or out? Energy went in. If the final condition of enthalpy is higher, if enthalpy goes up, energy went in. And guys, we know a name for that when heat or enthalpy goes up. Endothermic, right? Thermic is heat or enthalpy, and if energy is going in, then the final energy is higher, and conversely, if energy is going out, the final energy is lower. So guys, if delta H is positive, that means the final energy is higher, energy goes in, we are in the system, energy goes up, it takes in heat. That is technically the definition of an endothermic process, when enthalpy is increasing. And then guys, conversely, if enthalpy is going down, then it gives off heat, and that's exothermic. Now I'm really, really glad we didn't rush through this. That would have been a mistake. Y'all good? Questions on this? Because this is about to get mathematical. You guys okay? Okay. So guys, now that you have this idea of energy going in or energy going out through the avenue of enthalpy, guys, now what we need to do is we need to quantify this. How much energy is going in and out? And guys, the answer to this is what are called thermochemical expressions. So guys, scratch this down. This is the same equation that you wrote down previously that says minus initial. Excuse me. Guys, the difference is now we're going to apply that generic concept to chemical reactions. And when we do, instead of saying final minus initial, we now say products and reactants. But do you see the connection? Where do reactions finally end up? Products. Where do they initially start? Reactants. So it's the same equation just applied to reactions. And when we do this, we can now talk about what are called thermochemical equations. So guys, let me give you an example, and I would encourage you to write it down. You're going to need it later. Guys, let me give you an example of a thermochemical equation. It looks like this. This is a thermochemical equation. I only put them because they matter in this case, and we'll talk about why in a second. Because Leah asks a good question. Do we need subscripts? And you understand that in this class, when you're taking tests, you don't. But you're going to find them meaningful now, so let's do. Phase matters in thermochemical equations. We'll talk about why in a second. So guys, once you have this written down, we're gonna muck this up and we're gonna talk about this. Y'all ready? You okay? You're good? Okay. So guys, what kind of reaction is this? But what kind of reaction is it? It's a synthesis reaction, right? You can picture, this is the reaction that made you giggle last year in lab when you stuck the burning splint in the tube of hydrogen. You went, and then yeah. Guys, that was this. So we had hydrogen gas trapped in the test tube, oxygen gas surrounding everything. You ignited it and you made water. So guys, this is a simple synthesis reaction. But your answer, when I said what kind of reaction is this, many of you didn't say synthesis. And frankly, I like your answer better because many of you said exothermic. Let's talk about that. Let me make sure I can write. So guys, when you said exothermic, what led you to that observation? The negative delta H. So guys, the idea is this. This is new to us. We've dealt with balanced equations for years now, but guys, we now have an additional bit of information. And guys, you've got to understand what this means. So, what this is telling us is that the delta H, and guys, how do we read delta H? What does that mean? Change in enthalpy, not heat, change in enthalpy. The change in enthalpy for this reaction is 400, let's just call it 480, it's easier to say. 480 kilojoules. So let's talk about what all this means. So first of all, what does it mean that it's negative? The energy is going up or down? Oh, wait, up or down? Up or down? Well, law of conservation of energy. So when we ask the question, is energy going up or down, what do we need to know? Where is our frame of reference? And guys, in chemistry, our frame of reference is always in the system, and our system is the hydrogens and the oxygens and the water. So guys, typically our system will be the atoms. So if our system is the atoms, here's our system, which direction is energy flowing, in or out? Energy is flowing out. So guys, the energy is flowing out of this, so that would make it exothermic. Does that make sense? Okay, now the question is this: how much energy is flowing out? It's obvious, just say it. 480 kilojoules, right? But guys, here's the question. Does that mean that any time we burn some hydrogen, we are always going to get 480 kilojoules out? No. If you burn a little, you get a little. If you burn a lot, you get more. So guys, how much stuff is necessary to release that much energy? 2 moles and 1 mole and 2 moles. So guys, these thermochemical equations are always written as balanced. So when they give you the energy for these thermochemical equations, it's always the amount of energy gained or lost as the reaction is written. So if we doubled the amounts, we would double the energy and so on. Does that make sense? Okay. Now guys, what about this? Oh, you know what? We're going to approach this differently. Let me clean up my mess, and then I've got we got 2 more thoughts to go before we move on. So, guys, are you comfortable with what we've said so far? Okay, now an important question. Where does the energy come from? When you burn hydrogen and oxygen to make water, we understand it gives off a pant load of energy. Where does it come from? Yeah. Okay, so what are you suggesting then?
I'm suggesting that it comes from
So, but you mentioned quicker. Talk with me about quicker.
And then the product is liquid.
Okay.
So it's moving slower, so it's
It does make sense, but the problem is that may not actually be right. And so let's talk about it. What evidence would we need to say that in fact the products have slowed down? What would we need to know? The temperature. And we don't know that. So there is the possibility that this hydrogen and oxygen is at like 80 Celsius. And when it makes the water, it's also at 80 Celsius. And it hasn't necessarily slowed down. In fact, if this thing's giving away energy, it may actually be speeding up, and those could be moving faster. So it's not a function of speed. I love the idea, but it's not a function of speed. Go ahead. It's all about bonds. Guys, we've talked about this before, but we need to have this conversation now. Guys, it's all about bonds. So let's remind ourselves, and this is big, you got to remember this, guys. In order to break bonds, does energy go in or out? Imagine a rock, and if you want to break a rock, what do you have to do? Add energy, right? Guys, to break something, you have to hit it. So guys, in order to break bonds, we have to add energy. I would encourage you to write this with me. These are our reactants. But guys, in order for this reaction to take place, what has to happen for the hydrogen and oxygens? What do they have to do before they can make water? They got to get away from each other. So we've got to add energy here, and energy there to break these things apart. Then, guys, once we've done that, and once we've broken these bonds apart, then we get two water molecules. So if energy goes in to break something apart, what then happens when bonds form? Energy comes out. So this is going to release energy. So guys, once you're done writing that down, don't miss this. So energy, you guys ready? Energy comes out when those bonds form, right? So the question is this: how much energy is released? And hear me close. How much energy is released when those bonds form? And the answer is 483 kilojoules more than went in to break those bonds. Just a minute. Did you catch that? How much energy came out? And the answer is 480 kilojoules more than went in to break these bonds. So guys, let's draw that, and then Leah will talk. So guys, I'm going to have to put this down here in the corner, but I would encourage you to draw just tall. So guys, what we've got is this. About halfway up your energy graph, draw this. And here's what we've got. We've got two hydrogens and one oxygen. These are our reactants. Now guys, in order for those reactants to turn into products, what has to happen to these reactants? Energy goes in or out? In. And we draw in as up. Now guys, how much energy goes in? We don't know. We'll figure it out on Thursday, but we don't know right now. We don't know how much energy goes in. We just know energy goes in. And when energy goes in, what are we going to put on that line? What do we have? No. We have not ions, atoms. They're not losing electrons. So we have 4 hydrogen atoms and 2 oxygen atoms. And they take their electrons with them, so they're not ions, they're actually back into their monatomic states. Then what happens to these dudes? What do? They make water. Now guys, don't draw anything yet, but let me ask you, where are you going to draw the horizontal line that will then represent the products? Does it go above, at, or below the reactants? Below. And it's down here. And guys, forgive me, I'm out of room to the right, so I'm going to have to like draw to the left. It's not good form, but it's going to have to do. These are two water molecules. Now the question is, just a second, Caleb. Now the question is, what is this elevation? 483 kilojoules. So guys, we don't need to know the specifics. We don't need to know how much energy goes in to break apart the hydrogen and the oxygen. We don't need to know how much energy is given off when atoms turn into molecules. The only thing we need to know is energy goes in to break it apart and energy comes out when the bonds are formed. And the difference between the starting and the ending point is simply 483 kilojoules. Leah, go ahead.
Do we still not know where the energy is coming from, though? Because the different amounts went in, where is the extra energy?
And the answer is this. These bonds are weaker than those. And that's why the reaction happens in the first place. These weaker bonds break, these stronger bonds form, and the net result is something that has lower energy and is therefore more stable. And that's what we have going on here, is that the energy of the system is going down. And you're going to find out once we get into chapter 19 that that's always the case. That every time a process takes place, the energy of the products is always lower than the energy of the reactants, if it happens spontaneously, and we'll talk about that in chapter 19. Caleb, go ahead.
So how would we know that those reactions go lower, those products go lower than reactants?
Yeah.
How much energy?
That's a good question, and the answer is right here. So, and that was what I was hoping to drive home with this, is that in a thermochemical equation, that number simply tells you the difference in energy between the reactants and the products. And if this is negative, the products will be below the reactants. We don't know how high this is. We don't know how far the drop. The only thing we know is that. And that's what the thermochemical equation gives us. Is that okay? Go ahead.
So we will always have the delta H on the thermochemical equation. Like we won't have to find it.
No. And that's actually what we're going to start doing. That's Alice, really neat you picked up on that. The question we're about to ask is, where do these numbers come from? And the answer is two things, either from experimentation or computation. And I'm going to teach you experimentation today in preparation for Thursday's lab. And then on Thursday in lecture, we're going to do the computation. But that's exactly where we're headed with this. Good for you. You guys settled on this? Now, guys, do this with me. I'm going to just do it right over the top of this mess. Guys, change the L to a G. You know what? Hold on. I hope I can do this, because if I can get rid of... Oh, good. It worked. Okay. I had to make a little less of a mess. So change the L to the G. Here's my question. Changing that L to a G, don't think. Don't talk. Think. How does it change your graph? Changing your L to a G, how does it change your graph? Think about it, and then we'll talk in a second. While you're thinking, I'm going to change colors. Oh, let me do this. Okay, so change this to a G. Do you understand the question? What are your thoughts? Changing L to G, how does it change the graph? Go ahead, Robbie.
Well, I mean, if it's so since the I'm assuming that I'm pretty sure that the delta H is the same.
It doesn't.
It does.
It does not. This changes.
It changes.
Yeah,
Oh,
yeah,
so
yeah.
I mean, so the product will go up because they have more energy.
That's it. Stop right. That's it. So, yeah, so the idea is this. The reactants aren't going to change, right? All we've done is change the phase of the products. So the idea is this. The same amount of energy has to go in to break the reactants apart, right? But then the question becomes, what is the difference between a gas and a liquid? And so when we talk about the difference of energy in a gas and a liquid, we're talking about then the energy in the products, which means this is going to change. The altitude of the products is going to change. So guys, if this is a gas, do gases have more or less energy than liquids? More. So if this has got more energy, that means that our water molecules would be somewhere at a higher energy state, and consequently, what happens to the value of delta H? Smaller. Does that make sense? Do you get the idea? Guys, if you want to think about it the other way, think about this. If this makes more sense to you, guys, this right here represents water as a gas, steam. But if you want to take steam and turn it into liquid water, what do you have to do? Let it lose energy, cool it down, right, guys? Where does condensation happen? On cold surfaces. That's why the windows of your car become like frosted, because the window is colder than the surrounding moisture, and the moisture can deposit onto your window and lose energy, and it's that loss of energy that allows it to turn into a liquid. Literally, the humidity in the air is dumping energy into the glass of your car, and it sticks as it liquefies. Yeah.
Does that mean if you took the liquid reaction and turned it into ice, you do the same thing with the gas and they have the same enthalpy change?
Oh, help me with that. Say that again.
If you took the water as a product,
So if you took this,
the water, not the water vapor,
oh, this, so the liquid water,
you froze that
okay.
to ice,
Are we in agreement then that it would do that even more? Okay, keep going.
could you do the same thing with the water vapor and freeze it into ice and do the same ratio or same resistance?
Okay, so let me just label this ice. Okay, and are you saying if we call this energy change 1 and if we call this energy change 2, are you saying are those the same? If that's your question, the answer is not even close. The amount of energy that, say you've got some fixed amount of water, a gram of water. If you've got a gram of water, the amount of gram of ice, if you've got a gram of ice, the amount of energy necessary to melt a gram of ice is insignificant compared to the amount of water needed to boil a gram of water. Boiling is way more energetic than melting. Why? Yeah, that's it. So the idea here is if this is ice, what do you have to do to get it to melt? No, that's boiling, and that's the point. What do you have to do to get this to melt? Just get it to wiggle enough that the structure collapses, but you're not breaking the IMFs. You're just releasing it from structure, so the IMFs are still present. To boil it, though, that is where you're breaking intermolecular forces, and that requires so much more energy than simply breaking the structure. I'm scrambling in my brain to think of the numbers, and it's been so long that I can't come up with them, but it's significant. The difference is significant. So guys, you good on these ideas? Allow me then to summarize them for you. Given the conversation that we just had, these ideas, and one that we didn't talk about, but let's do, should be okay. And guys, do this. Don't write these down. Just join me. And then if you need a moment to write them down, we can. So guys, idea number 1 is this. This is what is called, and I've been open with you. I don't remember the difference between extensive and intensive, but enthalpy is extensive. What that means is the more stuff you burn, the more energy you give off, right? We talked about the idea that 480 kilojoules is released when you burn 2 moles of hydrogen, 1 mole of oxygen, get 2 moles of water. So the reactions are given, the energies given are for moles as represented. Guys, this we didn't talk about. Join me for this one really quickly. We said this is a synthesis reaction, right? Energy's given off. But guys, we know that the opposite of synthesis is decomposition. It's going the other way. And we can do that. So if we go the other way, what changes? The sign of the delta H. If 400 joules is released when water's formed, 480 joules has to go in when water's broken down. And then finally, as we said, these are phase dependent, and we demonstrated that with liquids and gases in the previous example. So if you want a second to write these down, I'm happy to wait. If you don't, we're going to keep going. Y'all okay? Can we keep going? Okay. You sure? We good? Okay. So guys, we're going to do some math. Some stoichiometry. Guys, it reads like this. And then, Alice, we're going to get to your question. So guys, it says this. When 4.5 grams of methane, you don't need to write this down. But guys, how much heat is released when 4.5 grams of methane is burned in an open container? So first of all, if it's burning, what do we also know to be present? Oxygen. Good. Now, what does it mean that it's an open container? What can it do? Can do work. We know that it does. Burning, combustion, expansion. So in an open container. So it's basically burning 4.5 grams of methane in a Bunsen burner, right? Methane is Bunsen burner gas. And if you were to burn 4.5 grams of methane in a Bunsen burner, the question is, how much heat is released? Now guys, notice what I did, and I did this purposely. We're talking about an open container, right? What does that make us think of? What can't happen? Work. And if work is off the table, then we're left with heat in the absence of work, which we call enthalpy. So, guys, I was purposefully sloppy with this because we do this. We are actually not talking about heat. We're talking about heat in the absence of work, which is enthalpy. But guys, understand, in this context, we can use the terms interchangeably because we never in this class, and many times in chemistry, we just disregard work, and therefore we can just think of heat. So we can say heat or enthalpy and use them interchangeably. Okay. So guys, in order to solve this problem, what do we need to know? This. I still don't think you need to write it down, but I would like you to solve the problem. Figure it out. No, really, figure it out. Like, write stuff. Guys, solve the problem. And guys, again, remember that even this early in the year, you're training yourselves. Some of you had this experience on the test that we just took. You read a question. Your first response was, I have no stinking idea what this means, and you froze. Guys, don't let yourself freeze. You read this question, you go, I have no stinking idea what it means, and then guys, the next thing that you do is the most important thing you're going to do. You've got to get over this paralysis, and you need to start developing strategies that allow you to solve problems. Now guys, how are you going to solve this? What's it going to look like? Dimensional analysis. Draw a line. And guys, if you haven't drawn a line, I don't care what you can do with your calculator, you will get 0 on the AP test. Please don't train yourself to grab your calculator first. Answers without support are worthless. Draw a line. You guys done? So let's draw a line. Oh! Drawing a line requires something that will let me draw a line. So guys, we're drawing a line. And when we set up dimensional analysis problems, we always start with the goal. What are we solving for? How much heat? That's kilojoules. So then, guys, the question becomes how much energy, how much heat is released when what happens? And the answer is we combust 4.50 grams of CH4. So now, guys, we've got to figure out a way to get from grams into kilojoules. So where do we go? Moles. 16.0 grams of CH4 is 1 mole of CH4. So now, guys, we're in moles. And that is helpful to us because we've been given a thermochemical equation. And what we then know is this. For every mole of CH4 that we burn, how much energy comes out? So 890 kilojoules. And guys, I know that some of you said negative. Bear with me. And we'll talk. $250? Okay. So guys, the answer is to two significant digits, 250 kilojoules. Y'all good? Because we need to have sort of a high-level conversation. You okay? Okay, so guys, the high-level conversation goes like this. Is that value negative? And the answer, well, it's not. Sorry, let me ask this different. Should that value be negative? And the answer is no. What word in the question means that that value doesn't need to be negative? The word released. Guys, the word released implies direction. And guys, in this class, but in this unit, direction is critical. So direction is indicated by sign. But in this question, we see that the word released implies direction. So if direction is implied in the question, the answer only needs to be the amount that's released, not the direction it's going. Now, what if the question says this? What if it said, what is delta H when 4.5 grams of methane is burned? Then does that need a sign? It does. And that's the difference. Now, guys, what you're going to see later in this unit is we are going to be talking about when we need signs and when we don't. And it comes down to whether or not direction is implied. Does that make sense? It's kind of like the difference between somebody coming up to you and saying, how much weight have you lost? And man, you look different. Has your weight changed? You know what I'm saying? If they ask you how much is it, 20 pounds, they know you've lost it. But if they say, how much is your weight changed? You need to go, yeah, I've lost about 20 pounds. It's you need to imply it. You get the idea. We good? Okay. So guys, anything else there we need to talk about? Now you understand why I didn't want to rush through the end of last time. You good? Okay. So guys, this then is the remainder of your homework. Did you get to write all these down? So we already wrote down like part of this. You did to 34. So then add 35, 39, 41, and 45. I'm sorry? We'll grade this as a whole, but we're not done. We're only halfway done, guys. You guys good there? All right. So getting rid of this and now transitioning seamlessly, check this out, into Alice's question. So guys, Alice insightfully asked, where do these numbers come from? And guys, I want to answer that question, and I would encourage you not to write this down. Where do these numbers come from? So guys, let me help you organize your thoughts. So this is a generic form. Again, don't write this down. This is a generic form of a thermochemical equation. We've got X and Y becoming W and Z, and there's an energy change associated with that that we represent by some delta H in kilojoules. So where do the numbers come from that populate this part of the thermochemical equation? And guys, the answer is this. What we're talking about is, where does this enthalpy change data come from? And guys, what you're going to find out is it can actually come from two places. One of the places that this data can come from is empirical. And guys, what does empirical mean? Experimentation. And guys, when we get this data from experimentation, we are carrying out a process called calorimetry. And that's what we're going to talk about for the rest of the day. Then there's another way to gather this data, and it is computational through what is called Hess's law. Now guys, you are going to be accountable for Hess's law in two different forms, and we're going to talk about this Thursday during this class period. Guys, we can attack Hess's law through a process of manipulation, or we can attack Hess's law through a process of computation. And the AP authors expect you to do both. They will limit your choices based on the data that they give you, and you'll have to do these through one or the other. But I'm going to, well, actually, it's really cool. About 5 years into teaching this class, I realized that these are actually the same. And that's how I'm going to present it to you. It's actually really neat when you get it. But guys, this then is how this is going to go. Where do these numbers come from? Sometimes through experimentation, calorimetry, sometimes through math called Hess's law, and that can happen through manipulation or using equations in computation. So this is today, this is next time. You guys good? Okay. So guys, time to deal with calorimetry. Here we go. So guys, before we get into this, we have to define some terms. Write this down. So guys, when we deal with heat, there are two ways that we deal with heat. And when we say deal with heat, we mean quantify how much heat a substance can absorb. Now guys, let's be clear on this. We'd better talk about this. Guys, what happens to a substance when it absorbs heat? How do we know a substance has absorbed heat? Temperature goes up. But guys, physically at a molecular level, what is happening when the temperature goes up? Molecules move faster. Now guys, here's the thing you've got to understand. Not all molecules speed up the same amount with the same amount of energy. Did you know that? Let's talk. So guys, there's a substance on Earth that is amazingly resistant to energy change. You can dump in a pant load of water and its temperature barely changes. Do you know what that substance is? Water. Guys, water is freakishly resistant to temperature change. Guys, that's why San Diego is so mild and Moab is hell most of the year. Have you thought about this? Guys, the most boring job on the planet is to be a weatherman in San Diego. It doesn't matter if it's June or January. Today, guys, the high is going to be 70 and the low is going to be 60. Every single stinking, well, not exactly, but guys, the temperature changes in San Diego only vary about 15 or 20 degrees per day, and it doesn't change much between January and June. Why? The ocean. Guys, it's the ocean. So when the sun is shining on San Diego, where's most of the energy go? Into the water. And the water, its temperature doesn't change that much, but the water is like this huge heat sink, and all that energy goes into the water, and that then stores all that energy. So it doesn't get that hot in San Diego because most of the energy goes into the water. But then what happens when the sun goes down? the water re-releases that energy into the air, and it warms the air back up, and it doesn't get that cold at night. You ever been in Moab, like in October? Holy smokes, the sun comes up and it's 90 degrees, and the sun goes down and it's 20 below. Why? There's no water, there's sand. And guys, sand is not as capable of storing energy. When sand absorbs energy, its temperature goes way up, and when it releases that energy, its temperature goes way down. And because the heat of the temperature of the sand varies so much, the temperature of the air varies so much, and the temperature of the place varies so much. You see what I'm saying? So then the question becomes this: how do we measure a substance's sensitivity to changes in heat? And the answer is there's two. One of these is called molar heat capacity. So guys, write this down. A molar heat capacity is the amount of energy needed to raise 1 mole of a substance's temperature 1 degree Celsius. And as you write that down, you may be thinking to yourself, that sounds familiar. Just write it down. We'll talk. The amount of energy needed to raise the mole of raise 1 mole of a substance's temperature 1 degree Celsius. So what are the units for this? It is joules per mole Celsius. You could write it like this. But guys, it looks like the connection is this. The amount of energy in joules needed to raise 1 mole 1 degree Celsius. So the units are the definition. And guys, it is abbreviated C sub m, capital C sub m. Now guys, I know I mentioned that for some of you this may sound familiar, but I don't want to help you make connections yet. Let me give you the other unit, and then we'll talk. Guys, the other one that you need to know is what is called specific heat capacity. Or maybe you've heard it termed specific heat. And guys, as you're writing this down, let me ask, for those of you that have taken physics, have you done either one of these before? Cody, you have? Josh? You did? Really? Good for her. Yeah, that's awesome. Okay, so I'm going to treat this as if it's not familiar. So guys, let me define it for you. Specific heat capacity, which is also called specific heat, is the amount of energy needed to raise 1 gram of a substance's temperature, 1 degree Celsius. So guys, what is the difference between molar and specific heat capacity? The amount. For molar, it's a mole. For the other, it's a gram. But guys, does this one sound familiar? The amount of energy needed to raise 1 gram of a substance's temperature 1 degree Celsius? It's the definition of a calorie. If the substance is what? Water. So guys, the calorie is defined as the amount of energy needed to raise 1 gram of water's temperature 1 degree Celsius. So the specific heat, thank you. So guys, the specific heat of water is actually 1 calorie. And that then is the definition of the calorie. So guys, the units for this are joules per gram Celsius. You guys just... And guys, I forgot to have you do this, but I'll just give it to you to save time. Guys, this is abbreviated C sub S or small c. And guys, I'll write it down for you. It is actually on the AP equation sheet, but I don't want to spend the time to have you look it up. Let me just give it to you. Guys, the equation for this then is this. Write it down. Q is what? Heat is equal to, I want to give it to you the way it is on the sheet because I learned it differently in college. MC delta T. So guys, Q is heat. What's M? Mass. What is C? Specific heat. And then what is delta T? Temperature. Now guys, watch. Let's make sure you're making the connection. So here's what we know. The specific heat for water is really big. So if we add some heat to water, say we've got a fixed mass, if we add some heat to water, how much will the temperature change given this equation? Well, not much, because if this number is big, the temperature's, let's do this, let's solve it for delta T. So we've got Q is equal to M divided by C. So the idea is this. If we've got water, water's got a huge Q value. So if we add a bunch of energy to water, because its specific heat is high, the temperature is not going to change much. But if you've got sand, sand has got a smaller specific heat, and as a result, if you add the same amount of energy, the temperature is going to change a lot because you've got a smaller specific heat. You get the idea? Guys, that's also why if you ever touch a piece of metal and it feels cold, go ahead and try it. If you touch a piece of metal and it feels cold, it's not cold, it's room temperature. Guys, the reason metal feels cold is because the specific heats of metals are very, very low, and they just suck energy out of your skin and it feels cold. But they're not cold, they're exactly the same temperature. I mean, feel both. Feel the tabletop and feel the leg. Does the leg feel colder? Yeah, it's because its specific heat is smaller.
So if we were to like take some sort of thermometer that can measure that and put it on the electric.
We barely have time to do this, but I will. Oh, are my batteries dead? Oh, my batteries are dead. That's actually why I bought this. It's a thermometer, and you can point it at stuff and shoot it, and it tells you the temperature, and you'd find they're exactly the same. Yeah, they're both in the room. They're both room temperature. You guys good on the idea? Okay. So guys, now let's take these ideas and let's put them to work. So guys, we are now going to talk about what is called coffee cup calorimetry. And I understand that in Utah County, you're already at a deficit. Hot chocolate cup calorimetry. When I first started teaching in Utah, it was Postum. Do you guys know about Postum? They used to call it Mormon coffee. It actually kind of tastes like coffee, but it's not coffee. And when I moved here in the early 90s, people drank it because they thought they were getting away with something. So, guys, all we're talking about here is an insulated container. Do not write this down. But guys, it used to be an AP that I had to teach you about constant pressure calorimetry and also constant volume calorimetry. You may have noticed in chapter 5 it covers both. Guys, they got rid of constant volume calorimetry, so we don't need to worry about it. You got to know this one though. And so guys, this is what you need to know about coffee cup calorimetry. So guys, coffee cup calorimetry is actually what is called constant pressure calorimetry. And guys, in a constant pressure calorimeter, functionally what you've got is an insulated container. The better insulated the container is, the more expensive the calorimeter. If you're doing this as a calorimetric chemist in college, you would actually have you'd have a thermos that is like crazy good. We're just going to use stacked coffee cups. It works pretty well. Then guys, in this calorimeter, notice what we've got. We've got a thermometer, we've got a stirring device, we've got a lid, we've got styrofoam cups, and then we've got stuff inside the cups. Guys, that's all there is to it. And because it's that simple, we're going to draw it. So let's do this together. So guys, you're going to want some space. You're going to make your coffee cup like the size of your fist maybe. But you're going to want a lot of blank space around this. So guys, this then, trying to picture how this is going to fit. It's still going to look horrible, but at least I want to try. No, I want it a little taller and a little thinner. Okay, so like that, and then we're going to put a lid on it, and let's stack it. So guys, that's meant to represent 2 cups. And then I have the advantage of being able to change color. So I'm going to put some water in there. And then I'm going to go back to black. You know what? I'm going to do that the way. Switching to red. That's our thermometer. And then switching to black, that's going to be our stirring device. So guys, this is functionally what a coffee cup calorimeter consists of. If you would like to label the parts, you're certainly welcome to do that. What you are looking at is stacked coffee cups. And then you've got a lid, you've got a thermometer, and then guys, in lab, what we're going to do is our stirring device is actually going to be a long piece of metal wire that we're going to throw a loop in that you can pass down over your thermometer, and then you're just going to slide it up and down your thermometer. And what that allows us to do is only puncture the lid in one location. And guys, this is all there is to it. This is actually an amazingly good constant pressure calorimeter. Yeah.
So like, is coffee cup
You'll probably see both, but you can use, so the term coffee cup calorimeter sounds slang, right? You can use it. So on the AP test, this is an accepted way of referring to this. Okay, now guys, regardless of how you've structured this, this is the conversation that we need to have. We need to define our system. We need to define our surroundings. We need to define how this thing works, and we need to define the math involved. You know what? Let me add one more. You guys are kind of behind me, right? Okay, I'll just put it down below. And we define its usefulness. Man, I wish this worked. Even how to put it better. It's like a mental. Oh, there we go. Up. 9 volts. This is 9 volts. I think I may have some. Who uses this? I guess I don't. Never mind. Okay. You guys good? You all caught up? Okay. So guys, let's pick the low-hanging fruit first. Ready? Let's talk about the usefulness of this. It should come as no surprise that if there's water inside this thing, what's the only thing this thing's good for? Aqueous chemistry. Guys, this has to happen in the presence of water, so the only thing that this is good for, I'm going to go blue, the only thing this is good for, Aqueous. Guys, the only thing this is good for is aqueous chemistry. So what does that include? Well, that includes precipitation reactions. That includes acid-base reactions. That's what we're going to do next in lab. That includes redox reactions. And it also includes solvation processes, where you take things and dissolve them in water and figure out how much energy is lost or gained. And that's actually what we're going to do in 2 labs. So guys, we're going to use this for acid base first, and then we're going to use it for solution formation second. But the only thing this is good for is aqueous chemistry. So now guys, let's do this. How do these things work? And it's really based on this idea of aqueous chemistry, but simply what you're doing is this. Well, maybe it would be better to define system and surroundings first, and then let's talk about how it works. So guys, I'm going to give you system. System is this. That's it. Coffee cup calorimeter, guys, your system is simply the atoms that are doing the reacting. End of story. So, guys, what was that? You okay? That's what we need to talk about. So, guys, if the system is the atoms well, not if, it is. The system is the atoms doing the reacting. So, guys, if that's true, what are the surroundings? What are surroundings? Everything else. But guys, this is where we get tricky. Because here's the deal. If we do a reaction in say it's exothermic. If we do a reaction in a calorimeter and that reaction is exothermic, will that reaction feel hot or cold? If we do an exothermic reaction, will it be hot or cold? Hot. It's going to give off energy. It's going to give off heat. So guys, that reaction will be hot, and where will that energy go? If we're in the system and we do the reaction and it's exothermic, where does the energy go? Everywhere, right? It goes into the universe. But guys, that's worthless to us. If we're just bleeding energy into the universe, there's no way for us to track that down. And consequently, calorimetry becomes a worthless pursuit. So guys, here's what we do. We take the universe and we focus it. And how do we focus down the universe? The answer is a coffee cup. It's really the case. Guys, here's what we do. We make our surroundings only the water in the cup. But guys, we understand that the universe, the surroundings is the universe. It's everything that's not the reaction atoms. But here's what we do. We create our own little universe inside that cup. And how do we keep our little universe from playing with the real universe? We insulate it. Now guys, let's be honest about this. We know we can't do this perfectly. If we carry out an exothermic reaction in this calorimeter, where is the energy going to go? Into the water. What's going to happen to the temperature of the water? It's going to go up. And then what if we come back tomorrow and stick our finger in the water? It's going to be room temperature, right? So here's the idea. If this water starts room temperature and we do an exothermic reaction in that water, the temperature of the water is initially going to go up. But then after a day, the energy is going to leak into the whole universe, and eventually we'll end up back at room temperature. Now here's the trick. Guys, what happens is this coffee cup buys us time. So what we can do is we can do the reaction and stir this thing like crazy. And when we do, the energy goes from the reaction into the water, and the water temperature goes up. and eventually it'll stop. So the water temperature goes up, and we measure this temperature, and we measure this temperature, and we can measure the temperature change. And if we do that quickly enough, the energy will stay in the water long enough that we can measure it, and then we don't care if it bleeds into the universe later. Do you get the idea? So guys, what would it actually look like? If the x-axis is time and the y-axis is temperature, when we actually do this reaction, the temperature goes up, right? And then what really happens over time? The temperature goes back down, but we don't care. Because we can be fast enough that we can grab this temperature, and that's the temperature change that we need, because that's representative of the energy lost. Does that make sense? Okay, so how then does this thing work? Well, it goes like this. Energy lost or gained by the reaction is equal to energy gained or lost by the water. That's how it, well, that is a mathematical representation of how it works. We're going to look at the math later. That's not the math. It does bring up, Leah, an interesting question we'll talk about in a second. So guys, as I wrote down that sentence, it's more important to hear what I said. How does this calorimeter work? And guys, this is representative of this. The idea behind how this works is we carry out a reaction in water. If that reaction is exothermic, where does the energy go? Into the water. What happens to the water? Temperature goes up. Now guys, what if the reaction is endothermic? Well, if the reaction is endothermic, which way does energy go? Into the atoms, and what are we going to see? The temperature drops. You get the idea? Okay, does that make sense, Leah? That's how it works. So now let's talk about the math. And guys, this is where we run into a problem. This looks like a mathematical equation, right? But guys, this mathematical equation is worthless to us. Do you remember why? You can't directly measure energy. But we can't. Not directly. But what can we measure the change of that leads us to? That's it. Guys, what we actually measure is changes in temperature, which then leads us to, is this the way I gave you the equation? MCAT, oh yeah, MCAT. There you go. That is the math that we're going to use. But guys, notice this. This is the MCAT of what? The water. Guys, make sure you're clear on this. This equation represents what is happening to the water. So now, guys, let's do this. If you've got a little bit of space, we are going to take these two ideas and we're going to mush them together. So here's what we know. First law of thermodynamics says this. The energy lost or gained by the reaction, let's do this differently. The heat lost or gained by the reaction is equal to the heat gained or lost by the water. Is that okay? Okay. But then the only one of these that we can actually track is the energy gained or lost by the water. But if we can quantify this, we can then quantify that. Does that make sense? So when we pull those things together, what we can say then is that the energy lost or gained by the reaction is equal to the mass and the specific heat and the change in temperature of the water. And we can bring those two together because we know that the gain by one is lost by the other, so we can infer the amount of energy lost or gained by the reaction by seeing the impact that that loss or gain had on the water. Does that all make sense? Then guys, let's try it. And it goes like this. Go ahead. Do you need me to go back to my picture? What?
Since this is like a volume contained, it's not pressure.
The lid does not seal tight. Yeah, so it can escape without doing work. Is that what you were asking? So, and this is one of the disadvantages of not doing the other kind of calorimetry. The other kind of calorimetry, which is not constant volume calorimetry, is called bomb calorimetry. And literally, you've got a sealed metal container that you dunk in a pool of water, and you run electrodes into it and charge it with oxygen. And then what you do is you put the sample in there that you want to know the heat of reaction for, and you put that in a container that can neither expand nor contract. It's constant volume. And then when you set off the reaction by passing a spark through it, that substance burns in a fixed volume, and the pressure goes through the roof. That's why they call them bomb calorimeters, because sometimes they blow up. And then what happens is all of that energy bleeds out of the container and into the water. So we're still using water as the surroundings. The difference is that thing can't expand. So, yeah.
So because you're measuring the surroundings,
Mm-hmm.
does your sign have to change?
And that's what we're going to talk about now. Guys, signs are critical. Read this with. Wait for a couple minutes. It says when 3.25 gram sample of sodium hydroxide was dissolved in a calorimeter in 100 grams of water, the temperature went from bing to boom. Calculate delta H for the solution process, and then notice what it says. Assume it's a perfect calorimeter and that the specific heat of the solution is the same as the specific heat of water. So guys, this is what we're saying. We've got a calorimeter, and how much water is in that calorimeter? 100 grams. So we've got 100 grams of water in the calorimeter, and we are going to take a 3.25 gram sample of NaOH, and we're going to slam dunk it in here. When we do, what happens to the temperature of the water? Does it go up or down? It goes up. Now guys, if the temperature goes up, what does that tell us about the dissolving of sodium hydroxide in water? It's exothermic. The question is, what is the delta H for this process? Do you understand what we're doing? We're going to get a number. Guys, some of you are getting fidgety and you're packing up. Don't. I just gave you all an I. You are now my students during Pride. Does that help you settle in? Because you're going to be here till 12:20. We got half an hour. We got all the time we need. You guys good? Okay, so let's focus. So guys, how then are we going to solve this problem? Well, guys, here's what we know. The amount of energy that's lost by the dissolving is equal to the amount of water, the amount of energy gained by what? What's doing the energy absorbing? The water. So guys, we can study that. Q is equal to MC delta T. We want to know how much energy the water gained. So what do we need to know about the water? The mass, 100 grams. Then guys, the next thing, and I think I may know your question. Let's finish this and then we'll talk. Then guys, the next thing that we need to know is the specific heat of water. It's on the AP sheet. It's 4.18 joules per gram per Celsius degree. Now guys, the last thing we need to know is what is the temperature change? 8.1? Can I subtract? Remember, I went to public schools. 8.1 degrees Celsius, and we do the math, and we get 100 times 4.18 times 8.1, and two significant digits, 3,400 joules. Now, guys, we've got all sorts of problems to iron out. We are nowhere near the answer. You had a problem.
Yeah, mine was just that the volume, the mass of the water was 103.25.
Good, and let's talk, because that's actually not the case. And here's the idea. The sodium hydroxide that we originally put in is the system. And if it's the system, it's not the surroundings. Consequently, the mass of the water is 100 grams. But if you back that up a little, Talmadge, that leads to another problem. Because when the sodium hydroxide goes into the water, it creates a solution. And the specific heat of a solution is not the same as the specific heat of pure water. And that's what this is about. No, that's what this is about. Assume that the specific heat of the solution is the same as that as pure water. Technically, if we were really doing this perfectly, we would have to account for the fact that the intermolecular forces between the solute and the water change the specific heat of the water a little bit. They'll never ask you to do that. Is that okay? Guys, but do you understand why the mass is not 103.25 grams? Is that okay? Okay. But guys, even with that, this is still wrong. Why, Addie?
Because that's the
What does it
heat
need?
by the surroundings.
Yeah.
So the inverse of that, the opposite of
Yeah.
that. Needs to be negative.
It needs a negative. It needs a sign. So guys, let's talk about why. What happened to the temperature of the water? Did it go up or down? Temperature of the water went up. So what happened to the system? It lost energy. The energy went into the water, the temperature of the water went up. And guys, this is counterintuitive. If the energy of the water goes up, the energy of the system goes down, and that makes this negative. Does the negative have to be there? Yeah, because there's nothing in the question that assumes that it's exothermic. And we're still not right. Because what is the question asking you to solve for? Kilojoules per mole. And guys, all we know is joules for how much sodium hydroxide? 3.25 grams. So guys, we now need to do some dimensional analysis because we are solving for kilojoules per mole, and what we know is joules per 3.25 grams of sodium hydroxide.
Good day, Tiger.
So how do we fix this? Well, 1,000 joules is 1 kilojoule, and then 23 and 17, it's about 40. So 40 grams is 1 mole of sodium hydroxide. Now we're closing in on the answer. So 3,400 divided by 3.25 times 40 divided by 1,000, and I get 42 kilojoules per mole. And that is the heat of solution for sodium hydroxide that we could look up in a book, that we could find on Wikipedia. This is the number. Yeah. No. Yeah, it's negative. Yeah.
So we just change the sign after and then we don't.
No. I just forgot to put it. It should be negative. Yeah. You guys okay? Okay. Now, guys, we're in a similarly weird spot. We haven't finished everything, but we need to look at the homework for this. So let's talk. So guys, here's where we are. Just write this down. We are going to do the ones of these that we can. Did you get to write them down? But then, guys, in addition to that, what we're also needing to look at, and I'll explain to you how we're going to chunk this in a second. Guys, it's time to now start thinking about summarizing chapter 19. So write it down and then we'll talk. Guys, chapter 19 is going to be the same 4-quadrant system that you used for chapter 5. But guys, this is how are you okay? Can we talk about how we're going to handle this? So, and this is just an honor call, y'all, but I need you to do this. So when I see you Thursday, we are going to grade the homework over enthalpy, the previous assignment that you wrote down. That's going to be due. Does that make sense? Okay. But then, guys, we are not going to grade any of this. But it would definitely be to your advantage to have looked at those of them that you should be able to do given what we know about calorimetry, okay? But we will finally grade all of this on Monday. And your Chapter 19 summaries will also be due on Monday. So guys, in summary, here then is where we're at. On Thursday, we will grade the homework that we sort of started last time in its entirety. Then we will finish what we need to know about Chapter 5 by looking at Hess's Law. That's the end of Chapter 5. Then, guys, on Monday, we will grade all of this, and you'll turn in your Chapter 19 summaries, and we will get into entropy and Gibbs free energy, which is what Chapter 19 is about. Do you see how we're going to split that up? So, guys, that's the end of our day. Sit tight for a second. I frankly don't know who of you should be leaving for Pride. Obviously, I was